So now we'll make an improved active half-wave rectifier, and we'll see in the circuit that we'll require two diodes for this. So let's start with the same thing, our 741 biased properly, right? And in this one now I'll connect the two diodes in the feedback loop. So the first one forms the resistive feedback, right? So from pin number 6 through a 10 kilo ohm resistor, right? And this will then be connected to pin number 2. So let's connect it here, number 2. And now the signal is also given at the inverting input, right? So another 10 kilo ohm resistor here, and the input signal will be given through this. So I've connected the input signal, right? We'll use one more diode to form the second negative feedback arm. So let me connect it here, and then I'll connect it to both. So here pin number 6 to pin number 6, and so let me take this one out and connect it from here. So pin number 2, so this is the second arm of feedback, and this resistor I can probably connect directly here at pin number 2, right? Okay, so that should be enough, right? And now we have already given the signal, so we have to see the output. So let's first connect the oscilloscope to the input. This is my input, and I'm using the same input, 2 volts amplitude, peak to peak, 4 volts and 1 kilohertz, right? And now there is the second channel of the oscilloscope, and we will connect this. Again we are taking the output from the diode, right? Diode resistor combination. So let me connect it here, and most important in this case, it's an inverting amplifier. That means pin number 3 needs to be grounded. If we don't ground pin number 3, nothing's going to happen as far as the operational amplifier output is concerned, right? Okay, so this is our circuit, and now let's see what is seen on the oscilloscope. Okay, so again same as before, yellow is my input, blue is my output, right? And now as you can see, it's still an active half-wave rectifier. So we have the original signal, we have the rectified output here, right? One thing that we wanted to see is if we got rid of the glitch. So as you can see here, right, at the crossover points, the glitch seems to disappear. It's actually not there, at least at this frequency. Its magnitude has been reduced to a great extent, right? What we can also see is the actual operational amplifier output at pin number 6, right? So let's do that, and here we will see that interesting feature that earlier, where in the cutoff zone, when the operational amplifier is going to negative V saturation, here it's actually up to the forward drop of the diode. So if you can see, the minimum value is not going to minus 13 volts, it's only giving to about 600 millivolts. The upper side or the rectified side output is still the same, the 2 volts from the input signal plus 0.6 volts that is required to activate the diode or forward bias the diode, right? Okay, now I'll connect this channel back to rectified output, and now we'll simply increase the frequency and see the effect of frequency on the glitch if, let's say, it reappears. So let's go for 10 kilohertz, right? And at 10 kilohertz, if you look very carefully here, you can see that there is a slight amount of deviation from the ideal behavior. I can increase this scale just to see this effect more clearly, right? And one can see that there is slight amount of the effect. If we go further in frequency, right, something like 100 kilohertz, and you can recall that 100 kHz already the diode doesn't function properly. The operation amplifier, slew rate and bandwidth are all coming into picture. So as you can see, it's a very high frequency and the output is not really of any consequence. You cannot call it rectified output. The output wave